And also if you teach signal processing and you want to use different methods, so it contains, it doesn't go into too much depth, but it covers many of the algorithms that are fundamental in signal processing. So you can use this book. I recommend it. Okay, let's continue. Okay, so we already talked about adaptive beamforming, and I said that adaptive beamforming, in terms of derivations and definitions and all that, it's very simple because we already covered multi-channel signal enhancement. So multi-channel signal enhancement and adaptive beamforming are very similar. But instead of using the relative steering vector, which is the relative transfer functions, just like we mentioned in the multi-channel signal enhancement, we use steering vector, which is direction, only direction. This is the difference. All the other things are very similar. And because we use directions instead of relative transfer functions for this adaptive beamforming, we can also inspect what happens in examples to the beam pattern, just like we did for the fixed beamforming. So for adaptive beamforming, we can also take a look in the beam pattern. Why we didn't work with beam pattern for the multi-channel signal enhancement? Because with multi-channel signal enhancement, we try to estimate the signal. So we can talk about mean squared error, MVDR, and so on, control of the trade-off between distortion and noise reduction, and LCMV with additional constraints. Also the LCMV, we put constraints on relative transfer functions related to interferences. With LCMV for adaptive beamforming, we put constraints on directions. You see? So the only differences are the definition of the steering vector. If it's actual direction in free field, or is it derived from relative transfer functions? This is the only difference. And then because we work with directions instead of relative transfer functions, we can explore how the beam patterns look like. Okay? Because the beam pattern takes into account directions, responses to directions. With multi-channel signal enhancement, we work with relative transfer functions, so directions are less important. Even though we can combine, we can say, let's design a filter, optimal filter for signal enhancement based on relative transfer functions, and let's see what happens in a free environment without any reflections. It's also possible. And then you can compute the beam pattern for the multi-channel signal enhancement. But it doesn't make much sense. But it's also possible, okay? If you like to explore what is the response to a free field signal that comes from a certain direction without taking into account its reflections, then you can see or take a look at the beam pattern, okay? So this part, you know, we don't have much time, but we don't need much time. Because everything that I'm going to present here, you already know. Because you know the difference. Okay, so if we continue here, we have the signal model, performance measures, the adaptive beamformers, which in the multi-channel signal enhancement, we call it optimal filters. So here we call it adaptive beamformers. And this part you can read yourself. We're not going to cover here. It's just examples about estimation of the SNR and direction of arrival estimation. These are topics by themselves. So it's out of the scope of this course. And if you like, you can read the slides. It's not too complicated, but I don't want to go further into these topics. So we're going to cover this part, okay? This part, which is similar to multi-channel signal enhancement. So the model, you see, the model is similar to the multi-channel signal enhancement, but instead of steering vector that is derived based on the relative transfer function, it's derived for free field environment. No reflections, only direction. And we have here, so we can define it here. Once this is the variance, the beamformer is the same as a filter. This is the beamformer. And since now, in this problem, we know the correlations between sensors, the correlations between signals that are received in different sensors. We know that, so we know the statistics of the desired signal, and we know the statistics of the noise. So we can find an optimal adaptive filter, beamformer. So adaptive beamformer, that it adapts to the actual statistics of the desired signal and the noise sources. That's why if we use this information, we call it adaptive beamformer. But it's beamformer because we work with directions. This is the only difference, because we work with directions instead of relative transfer functions. So now we can define the performance measures. Will be exactly as the performance measures that we define for multi-channel signal enhancement. And also we will work with the beam pattern. So we can define the signal to noise ratio, the input narrowband, and broadband input SNR. See, very similar to what we did, multi-channel. We can define the output SNR. The output SNR, the output of the adaptive beamformer, which is exactly same definition that we had for multi-channel signal enhancement. Exactly the same. But instead of steering vector that we had over there, relative transfer functions, we have direction only, steering vector. But the definitions are the same. You just replace the vector D. Let's continue. Noise reduction factor, the gain in SNR, of course, and we have the noise reduction factor, narrowband and broadband, similar, okay? Similar to what we had, exactly the same definitions as multi-channel. And the distortionless constraint, so with multi-channel signal enhancement, we didn't have such a constraint all the time, only for distortionless response, which means MVDR, LCMV, GSC. Here, because we work with direction, which means we work with beamformer, so we always use this constraint. We keep it, okay, for the distortionless. But, okay. And actually, if we assume that we know the statistics of the desired signal, this constraint, we can relax it. Maybe we can say we can allow some distortion because we can control the distortion of the desired signal, even for a beamformer. But we allow distortion based on the direct path. Okay? So this distortion will be applicable in a free field environment without any reflections. Okay? So for fixed beamformer, because we don't know the statistics of the desired signal, we always use this constraint. For adaptive, we can allow more relaxed constraints because we can allow some distortion. We can control the distortion because we know the statistics, the correlations between different sensors. Okay? So we don't have with adaptive beamforming always to require that. Okay. Desired signal reduction factor, always also similar to what we defined for multi-channel signal enhancement, narrowband and broadband. Let's continue. Desired signal distortion index. Okay, because we know the statistics of the signal, okay, so what does it mean we know the statistics of the signal? You see, we know the spectrum of the desired signal here for the broadband. So we can define the broadband and narrowband desired signal distortion index. You see, for the narrowband, we don't actually need it, the spectrum of the signal, but for the broadband, we need it. That's why we couldn't define distortion index for fixed beamforming, because we don't know the variance of X, which is the spectrum of the desired signal. And we work with directions, okay? Any questions? Okay, let's continue. Mean squared error. Mean squared error, we couldn't define it for fixed beamforming because we don't know the statistic. But now, because we know the statistics of the signal, we can define narrowband mean squared error. Narrowband mean squared error, which composed of two components. One is related to the error of the to the distortion, to error in the desired signal, and one which is related to residual noise. The mean squared error related to the residual noise. So we have these two components. And you see that the component which is related to the distortion of the signal, see this expression, depends on the spectrum of the desired signal. This is the variance of XF, the source, the desired source, which is the spectrum of the desired signal. So the mean squared error depends on its spectrum of the desired signal. With fixed beamforming, we don't know the spectrum of the desired source or desired signal. That's why we cannot define this distortion. The mean squared error of the noise that is related to the noise, the correlation matrix of the noise. So this part is actually the variance of the residual noise. For fixed beamforming, we don't know the correlation matrix of the noise because we don't know the noise field. That's why we didn't define also this variance of residual noise. We can only define it if we assume a certain noise field. So for fixed beamforming, we assume either white noise or diffuse noise or combination using parameter alpha. And then we can compute the power of the residual noise. But for here, we can take actually the actual noise because we estimate the correlation matrix for actual environment. So we have this. Okay. Now, based on these performance measures, we can compute the optimal beamformers, optimal adaptive beamformers. So these beamformers, if we try to minimize the mean squared error, we get solution which is the Wiener beamformer, Wiener adaptive beamformer. So Wiener adaptive beamformer, it looks like this, which is similar to what we got, what we derived for the Wiener filter for multi-channel signal enhancement. The only difference is this vector D. But the other, you see, it's similar. Now we can have different expressions. You see, different expressions of the Wiener beamformer depending on how we estimate them. See, so different expressions, theoretically they are the same, but in practice they are not the same. Because once we put here some estimate, it's not the same. This is important. We talked about it. So this is an important thing to notice. So when you get also in your research some derivations, try to find equivalent expressions if these expressions are based on different methods of estimations. So it means that you have different algorithms to derive the beamformer or the filter. So we have different expressions. So it's important to derive different expressions when you have different methods in practice to estimate or to calculate your beamformer. They will generate different results in practical environments based on some measured data, especially when the environment is non-stationary. So it's important. But it's similar to what we had with the multi-channel. We just replaced the directivity, the steering vector. Example, so we can see an example like this, sinusoidal signal of length t, and we assume that the source comes from certain theta d, and we have two interferences, theta 1 and from theta 1 and theta 2. Okay, in addition to these interferences, we have thermal noise. Okay, so let's assume, see, all these derivations are very similar to what we did with the multi-channel signal enhancement. But let's assume that the desired signal comes from 70 degrees, and we have two interferences from 30 degrees and 50 degrees. And the thermal noise is very weak. It's only 1% of the directional interference. And we have 500 samples of measured data. Okay? So what happens? How does it look like? So in terms of noise reduction factor, gain, and so on, you're familiar with that. So if we have plots as a function of the input SNR, you see that the more sensors that you use, the blue line is for 10 sensors. The green is for 20 sensors. Red is for 30 sensors. And then the final is for 40 sensors. So you see the increase in output SNR, the gain in SNR increases, the more sensors that you use. Okay, so the noise reduction, just a minute. The noise reduction is here, you see? So the noise reduction factor increases the more sensors that you use. So you see gradually here, it's a 10 sensor, 20 sensor, 30, and 40. So the increase in noise reduction that can be obtained with additional sensors becomes smaller and smaller. Okay? Because the effect of adding 10 sensors is not the same. If you have a small number of sensors, then the addition is more significant. Here, it's less significant. It becomes less and less significant to add more sensors. This is the distortion. So you see when you add sensors, the distortion, the desired signal reduction factor decreases, and the distortion index also decreases. Okay, we are familiar with that. No problem. But I want to show you the beam pattern. How does it look? So this is the beam patterns, the beam pattern. This is for 10 sensors, 20 sensors, 30 sensors, and 40 sensors. So you see that the more sensors that you add, you see the desired signal comes from 70 degrees. Okay? So for all cases, we have gain beam pattern, which is the gain of the gain for a signal that comes from this direction, from 70 degrees, which is 1, 0 dB, in all these cases. And we have two interferences, one from 30 degrees and one for 50 degrees. So we have some kind of low gain, low response to these directions. So with 10 sensors, the performance is not that great, you see? So from observing the beam pattern, we see that the response to a signal that comes from 70 degrees is 0 dB, which is good because it satisfies this constraint. But we don't have any constraints on these directions, okay? Because it's a Wiener. And we also see that the beam pattern here is larger than 0 dB. So it means that if we have some noise sources that come from these directions, it will be amplified. But we didn't use this information. We just designed, what did we design? A Wiener beamformer. So a Wiener beamformer depends on the actual noise sources. So we have 3 noise sources. One from 30 degrees, one from 50 degrees, and one thermal noise. Okay? So when you design based on this information, it chose, because the small number of sensors, only 10, so the beamformer, the optimal beamformer, increases or amplifies noise from these directions. But because we don't have it, why not to increase this? It's okay. So this is the optimal beamformer. But if suddenly there will be an additional source from this direction, which is an interference, it will amplify it. So you see, whatever we design, it's based on the information that we include in the definition of the problem. If we don't include this information that maybe suddenly source interference can come from this direction, we didn't include it in the formulation of the problem, don't expect that it will be robust to such sudden appearance of interference from that direction, because you didn't include it in the definition of the problem. Okay. Now, if we increase the number of sensors, you see the more sensors that we use, the main beam become more narrow. Even though, did we have information on this? No. We didn't use such information. We didn't try to make the beam more narrow. But when we increase the number of sensors, we see that the beam patterns, the main beam becomes more narrow, and also the nulls here in the directions of the interferences, 30 degrees and 50 degrees, becomes more deep. So this makes sense. It becomes more deep. Why? Because when we increase the number of sensors, we can increase the amount of noise reduction. So this noise comes from this direction. So in order to increase the noise reductions, we put more deeper nulls in these directions. So you saw before that when we increase the number of sensors, the noise reduction increases. How does it increase? In the beam pattern, the nulls in these directions will become deeper, which means that we can suppress more noise from these directions. Okay? So when we increase number of sensors. But why did we get also that the main beam, the width of the main beam decreases? Okay? So it makes sense because there is no other sources. So we assume that the desired source comes from this direction, 70 degrees. So in order to make these nulls lower and also to reduce also thermal noise is uncorrelated. So it's just like, it's uncorrelated. So it tries to lower all the side lobes also. So it looks like it tries to lower noise that comes from any direction. So it tries to minimize the width of the main beam because there is no desired source from other direction. So it makes sense to make this main beam more narrow because we don't have any desired signal from another direction. So you see here that we just try to minimize the mean squared error between the desired signal and the output of the beamformer and what we get. Okay? If we use the MVDR, so with the MVDR, we have this constraint. No distortion in the desired direction. So we have this derivation, which is similar. So we see if we compare the gain in SNR, the noise reduction. So the more sensors that we use, here with 10, 20, 30, and 40 sensors. The more sensors that we use, we increase the noise reduction, and we increase the signal-to-noise ratio, the gain in SNR. And the distortion is 0 because it's MVDR. The mean squared error is reduced because we suppress more noise. So the MSE is only related to the residual noise. So the variance of the noise reduces because we reduce more noise. Okay, this is very easy, makes sense. What happens to the beam pattern? Okay, so if we see the beam patterns, because we use an additional constraint, so we don't have any distortion for this direction, so we get also for this direction, we get a gain which equals to 1, 0 dB. And the more sensors that we use, we have deeper nulls. Okay, just like what we got for the Wiener filter. Now, with the trade-off, we have an additional parameter, mu, that controls the amount of signal distortion and amount of noise reduction. So we can control through mu, and we have special cases. For mu equals to 1, we get the Wiener. Mu equals to 0, we get the MVDR. Mu larger than 1, we have more noise reduction at the account of the expense of distortion. And for mu smaller than 1, we have less noise reduction and less distortion. Okay, and then we have an example. I'll skip that. And we have maximum array gain. Okay, so we can find for fixed beamformer, we cannot define the maximum array gain generally because we don't know the noise field. So for fixed beamformer, we define maximum array gain for thermal noise, which is the white noise gain, and we define maximum array gain for diffuse noise, which is the directivity factor. For adaptive beamformer, we can find the beamformer that maximizes the array gain for the particular environment, for the particular noise environment. So if we use the particular noise environment, so we know the correlation matrix of the noise, we can maximize the array gain for this noise environment. We know how to find the maximum for something like that. We solve this problem, so we take the first eigenvector of phi v minus 1 multiplied with this matrix. Okay? So this is the maximum eigenvalue. Maximum eigenvalue is the maximum gain in SNR, the array gain, and the vector that maximizes the eigenvalue, the eigenvector of this matrix associated with the largest eigenvalue gives us the adaptive beamformer. And we can multiply it with any scalar, of course. Okay, so if we multiply it with any scalar, we get This is the adaptive beamformer that maximizes the array gain, gives us maximum output SNR. Just like we did with the multi-channel signal enhancement. Okay, so we can choose this. These are free values, free parameters that we can choose. Any parameters with, which are different than 0 will give us different results. So we can add some additional constraints or requirements to find these values. Just like we did with the multi-channel signal enhancement, but instead of relative transfer functions, we work with directions. Everything else is the same. LCMV, also here, we add some constraints for certain directions. We can put nulls in certain directions. So you see, we put nulls for certain directions. When we worked with LCMV for the multi-channel signal enhancement, we worked with constraints, steering vectors, which are derived from the relative transfer functions for each interference. Okay? So for example, if we are not in a free field environment, we are in a room like that, and I have a source like a loudspeaker or another source interference. So we need to know the relative transfer function, which includes all the reflections from the undesired source towards each sensor, which is information that we need to estimate or to find. If we know this information, we can suppress not only the direct path of the interference, but also the reflections. We can make a better job in reducing this interference. So when we add this constraint in the multi-channel signal enhancement, we take into account the reflections of the interference when they propagate to each of the sensors in the array. Okay? So think about radar or targets like that. Okay? So if we have radar and there is some interference that we want to suppress because it interferes with our radar system, so we can try to suppress that direction. But suppose that the interference comes from this direction, but there is also reflection through another path that comes to our system. So still it may affect our system. So if we can estimate these relative transfer functions from the interference towards the array, we can suppress also the reflections. And then we call it multi-channel signal enhancement. So that's what we talked before. If we don't know the pattern of these reflections, only the direct path, only the direction, so we use adaptive beamforming. Okay? So the question I ask you all the time, which one is better, to design adaptive beamformer or to design multi-channel signal enhancement filter? Okay? So this is always the question that you need to ask. So it depends on the information. If you have more information which is accurate, use it. If you have information which is inaccurate, or you don't want to, or you are not able because of the resources, so on, to obtain this additional information, then don't use it. But then you can compare specific examples when you have this information. One, when you have this information and it's accurate. When you have this information but you have some error in this information. Or when you derive a solution or optimization problem without using any of this information. All these three cases, you need to compare and explore the differences in the performances. Okay, so it depends on the application and the examples that you try to compare. Okay? So if we use this matrix of constraints, we define the LCMV for adaptive beamforming. So the optimization problem becomes minimizing or minimizing this, which means maximizing the array gain under this constraint. So we get the LCMV adaptive beamformer, which is similar to the adaptive filter, to the filter that we obtained for the LCMV in the multi-channel signal enhancement. The only difference is that the matrix C is different. Here, the matrix C takes directions into account. In the multi-channel signal enhancement, the matrix C takes into account relative transfer functions, which takes into account the specific environment, sources, including all reflections. Okay? Let's see an example. For the same example that before, suppose that we use the LCMV. Let's take a look at the beam patterns. So the beam patterns here, this is for 10 sensors, 20 sensors, 30 sensors, 40 sensors. So the more sensors that we use, we reduce more noise. Let's see it here. Okay? So the more sensors that we use, the noise reduction factor increases. The gain in SNR increases. The distortion is 0. Why the distortion is 0 with the LCMV? Exactly. We have the first constraint in the matrix is distortionless response. And we add additional constraints that suppress noise interferences from certain directions. So we don't have any distortion with the LCMV. Because LCMV, it's like MVDR with additional constraints on certain directions. And the MSE decreases. The MSE results only from the variance of the residual noise at the beamformer output. So if we increase more noise, the MSE decreases. No distortion. Okay, let's take a look at the beam pattern. Okay, so you see for 10 sensors, 20 sensors, 30 sensors, 40 sensors, in all cases, remember with the Wiener, the more sensors that we used, we had deeper nulls in the directions of the interferences, 30 degrees and 50 degrees. With the LCMV, we have complete nulls, no matter how many sensors that we use. Why? Because it's part of the constraint here, the constraint matrix. We put constraints, so the optimal beamformer puts nulls in the directions that we told it in the optimization problem, to put nulls in this direction. So we see we have nulls in these directions. But we didn't put any constraint or any requirement on the width of the main beam. So when we increase the number of sensors, the width of the main beam becomes more narrow, because it makes sense to keep only the signal that comes from 70 degrees. So with increasing the number of sensors, it can do that with a more narrow beam. Any questions? Okay, so this is a summary of the adaptive beamformers. So here we have the Wiener and VDR trade-off. So with the trade-off, we just added a trade-off parameter, mu. So for mu equals to 0, we get the MVDR. For mu equals to 1, we get the Wiener. And for mu larger than 1, we have the trade-off, how much noise we reduce compared to how much distortion. So this is adaptive beamformers that control the trade-off between distortion in the free field, no reflections. What is the amount of distortion compared to amount of noise reduction for the actual noise environment that we designed the beamformer. Now, the maximum array gain, also we have something like that, which is similar to what we get. And the LCMV, we add additional constraints on certain directions. Very nice. Now I would like to ask you a question. Okay, so you see, adaptive beamformers, we need to estimate the direction, and we need to estimate the direction of the desired source. We need to estimate the correlation matrix regarding the noise. We need to estimate the environment. So because of this estimate, and we have limited amount of information, sometimes this information, the correlation matrix is inaccurate. We cannot track fast changes in the environment and so on. So sometimes, because of that, we add here, the computational complexity is higher with adaptive beamforming because we need to estimate additional information. And sometimes we cannot adapt to the changes quickly. So sometimes we choose to work with fixed beamforming because it's simpler and with fixed. But if we can adapt to slowly varying information, slowly changing environments, and we can estimate these information that we use more reliably, and we can add some robustness to inaccuracies in the estimates, so we can get better performance. But not always, you see. So if we cannot do that, it's not that we use more information, we get straightforward, we get better performance. No, because we need to work to get this additional information. And if this information is inaccurate, we need to design more robust, to make it more robust to these inaccuracies. So robust beamformers, which I didn't cover too much here, I just talked about it. I talked about robust beamformer before and how to control what is robust and so on. But this is also a topic by itself. So you need to explore how to derive robustness to different inaccuracies. Inaccuracies in the directions of the arrival, inaccuracies in these matrices of the noise, and other inaccuracies in the sensors, in the responses, and so on. Okay? So beyond the material that we covered in the course, I try to give you a more broad understanding so you can continue and explore, and also take it to other research problems, other research topics, different areas. So you see that what you learn in one area can be useful also in other areas. Because many of the things, people that work in one area, they develop something. Many times there is overlap. Maybe the terms are different, but there is a lot of overlap between different areas in signal processing and in optimization and in other areas. So try to find this overlap because it will increase your understanding. And sometimes people that develop something smart or interesting in one area, but it takes time until people identify this innovation or this contribution in a different area. And people that find this equivalence and this overlap, it's a really nice contribution to bring innovations from one area to another. So this is also something that you can do if you're interested, to learn or combine innovations from different areas. And sometimes it's already known, so people make nice contributions, and it will contribute to your understanding when you see the equivalence or the overlap by using different terms. You see, oh, this problem is also this problem. It's just defined differently, but it's the same. The fact that you identify that it's the same, it contributes to your understanding. You see different approaches, different assumptions sometimes. Okay? Okay, so this is the material of the course. Do you have any question?